Jordan Smith. Packed
Stop.
up early.
Stop.
Sorry. Sorry.
Keep that to yourself. I'm not gonna say you actually.
Dang.
Okay, and come back to your seats. 5, 4, 3, 2, 2. Back to your seats. My group 1 is first. Group 1 actually stays up here. Okay.
What do you go back to your seats for?
Sorry, my first group. Alright, if you need space, there's like very little space in this canal, and then there's this big square space. Okay, so how does temperature play a role in rates of reactions? And
The higher the temperature is, the faster the rate of reaction is, because when there's a higher temperature, the molecules move faster and cause more collisions.
Okay, so increased temperature increases.
Rate of reaction.
Specifically, you said
Collisions.
before that, it's a domino effect. Increasing temperature does what to the molecule?
Makes them move faster.
Okay, so it increases the velocity or the speed of the molecules, and then what?
Collisions.
So increased collisions, but there's more to it than just increasing collisions.
They're with more energy.
They collide with more energy or with more force, and why is that important?
Chemical activation energy.
They need to meet activation energy. If you collide, that means you're going to react. Okay, so increasing collisions and increases the force of collision, so you're most likely to meet activation energy. So if you don't know that stuff, write it down. Okay, go.
Alright, so low temperatures. High temperatures.
So how do we know that it reacted?
Which bonds?
Okay, so they reacted, they made new bonds. High quality play acting there. Okay. Woo! Next group. Next group is my catalyst people. So you made, but yeah, so you would have increased the rate of reaction because you collided more quickly, so more collisions happening as you increase the rate of reaction. Alright, so how does the catalyst play a role? Go ahead and act it out first and then we'll talk. So, how does the catalyst play a role in rates of reaction?
Okay. Great. She picked me up. I was walking and then she touched me. So I was like,
So you're the catalyst? Okay.
That's right.
But how did you speed, so speeding her up means what in like AP Chem terms?
like changing.
Okay, so that changing or altering the reaction pathway.
To lower the activation energy needed. So that the collisions and more collisions. The bonds can overcome.
So it's not that more collisions are occurring, it's that more collisions are occurring effectively, meaning that they are meeting their activation energy so that therefore when they overcome activation energy, they definitely will react to form products. And so the catalyst is an external object that is reused, that's usually present throughout the entire reaction, so it's not going to be consumed. In biology, a good catalyst is what?
Enzymes.
Enzymes. All enzymes are catalysts, right?
Yeah.
So what's an example? Do you have an example?
It's in your stomach.
Lactase, helicase, catalase. We got all kinds of stuff going on, right? Okay. Huh? Anything with ace on the end is a catalyst. Yeah. Okay. Group 3. Am I involved?
Oh no, I think we're going to use this whole.
I hope you don't mind that there.
Jenna, we need your help. Okay, this is the wrong orientation, guys. Okay. Now this is the right orientation.
Oh, okay.
Now
We're over here.
bonded.
We're over here. Okay, so there's orientation. What else? There's 2 factors to effective collisions. Anybody want to chime in?
Activation energy.
Oh, good job. Okay, so we met activation energy. We collided with the correct amount of energy to allow for the collision to occur effectively. Good job. Woo! Okay. So, orientation, so correct orientation, it has to be occurring for the reaction to actually occur to be an effective collision, and you have to meet EA, activation energy, for the reaction to occur. So those are 2 factors that constitute an effective collision. Group 4. How do you calculate instantaneous rate? You want to tell what, or somehow explain what instantaneous means.
First, explain this. Oh, okay.
Well, it's how fast it's going at like any point in time, and the
How fast what's going?
particle or a reaction.
Reaction.
Reaction. That's right. You calculate the slope of like a tangent line to find this on like a graph.
Ready when you are.
All right.
This time.
Oh, okay.
Time at this instant.
Voting is put down.
Rise over run.
Yeah.
Get it?
Wow.
Oh,
You're not done?
oh. What does this mean?
What?
Tangent.
Tangent. Opposite.
Yeah, you guys might wanna.
Got it. Okay. Good job. Okay, so they're talking about rates of reactions are just basically sometimes they're averages, sometimes they're instantaneous. So if we pick a specific time for a rate of reaction, it's going to be actually calculated from a graph. So this is the graph, and so if I want to pick it at that point in time, I would draw a tangent line at that point, but you actually touch that, and then you would calculate the rise over run to figure out the slope of the line, aka the rate of the reaction. Group 5. You want basketball first or pick your poison, whatever works for you.
Alright, so instantaneous rates are the rates of reaction at any given time, and the relative rates are how the reaction progresses over time.
The change in concentration.
Go on this way.
Okay, go on this way.
Instantaneous, relative, go.
That makes sense. Okay, woo! Clay knows the director. Okay. So relative rates are going to be relative to other reactants and other products though. So that's one more thing to consider. So, how fast did you drive to school today?
What?
How fast did you drive to school today?
Your mom.
45.
I'm like 45.
Approximately
53.
53 what?
75.
Miles per hour. Okay, so in everyday life, our rates are distance over time, right? So rates are just always a comparative of something changing over the change in time. It's always relative to time. But in chemistry, we don't really go a distance, right? Well, you deal with reactions, right? So we deal with compounds, we deal with particles, we deal with molecules. And we can't really measure a whole lot about them except for maybe if they produce a gas, we can measure how much gas is produced. Maybe if they make a precipitate over an amount of time, or maybe if they change color, we can measure color change over time. But mostly we're really looking at concentration of those products and reactants over time. So all of our rates over time are going to be related to concentration. So I'm glad that your group said that because that's going to be one of our most important points. And you'll see it on graphs a lot and everything like that too, okay? So have your outline for me. I want you to add to your outline some of the notes from today. And then before we move on, I want to have you guys watch the video first. And this is a video from Honors Chem, so I think that you'll remember it. I don't know for sure. I don't know how great your memory is. But yes, the one about dating. So a relevant...
I really don't know.
This one, how to speed up chemical reaction, aka get a date.
Oh, yeah.
Okay. So this reviews some of the concepts that are some of the factors you can change that would speed up a chemical reaction. This is like baby kinetics. Baby kinetics means basically stuff you learned in honors chem, and then we'll go into big boy kinetics. Or big girl, whatever. You did rates. We did collision theory.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk to her class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have two important characteristics. One, correct orientation that allows books to be knocked from one's hands, and two, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I proposed 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I proposed that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing 2 particles together and orienting them correctly in space so that the 2 can meet at the correct configuration and allow a reaction to take place. So to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
All right. So we remember a little bit of that from Honors Chem, yes? Or is it kind of common sense? Kind of common sense, right? Okay. And that's what I was really hoping for. So you heard the word collision a lot. Basically, that's the collision theory. This is a lot of it's review from last year, but it's going to be a little bit more specific in terms of the terminology we use. So these are the notes I took on the video. You probably got similar things looking here. Yeah? Speak to me, people. Yes, great. Okay, so we're going to be really talking about the effective collisions that are occurring simply because they're colliding with the correct orientation and colliding with the correct energy. Because if you don't have enough energy in that collision, you will never surpass the energy of the bonds. And what is that energy of the bonds called? BDE? Bond dissociation energy, right? So the energy that's required is basically the energy of the bonds, because you need to be able to break every single one of the bonds so the atoms are free, so they can rearrange themselves to form the products. And so that's kind of relates back to thermochem a little bit, because we already know a little bit about that. This information, I don't know how much you need to really write, because it was on your reading guide, and you should have taken some of those outline notes. So opposing theory of how reactions occur is called the transition theory, transition state theory. So collision theory is just basically, hey, they collide, they react, we're done here. Transition state theory states that whenever they collide, they form this really weird middle intermediate thing that's very unstable. And if it's pushed farther, it will go to product, and if it's not pushed enough, it will kind of fall back to reactant. And I have a little image here for you in just a second. So it's a hypothetical transition state that's this intermediate that is unstable. And so it's kind of a hybrid between reactant and product, and so that's why we can't really isolate it very well, because it's very difficult to, it's just difficult to isolate. It's transient, it's not there for long. But we have a term for that thing. We call it the activated complex. This is a term I know I used last year. It's activated complex, and I'll show you where we have it on a diagram, but an alternate name for that is called the transition state. And it makes sense. It's the state of transition between reactant and product. How many good there? Eventually, I'll show you where I have some of the stuff on your notes that are printed for you, but it's just the main stuff I have on there. So these are two competing thoughts on how reactions occur. But we have to know both because they're still theories, and we have a lot of evidence to support both of these theories. They're just two different ideas of thought. So this, let me show you this first. This is the graph that indicates the activated complex and where it exists. You've seen this before. Yeah? It's just a reaction coordinate that we've seen a million times. So reactants collide. If they collide in the correct orientation, this black dot hits the red dot, and they form this activated complex where they're like a hybrid. And that's the transition state. That's the activated complex, because that itself is not stable enough to exist on its own. So if there was enough energy to make this, then you can assume a lot of times that it falls to the product side, to a lower energy state, so therefore it's going to make product. And if there's not enough activation energy to make that 100% of the time, it's going to fall back to form reactant. And what would you observe in the reaction? I was hoping you'd stay quiet. I was just hoping you'd say nothing, because nothing would happen. It would be an incomplete reaction because nothing would happen. So it's all based off collision and creation of this activated complex, and then you would form product if there's enough energy applied. So this is not a whole lot of new stuff, it's just the terminology. So what's happening here? This transition state is forming. You can read that, but I don't know how much, you can write what you need to, but just read it at first to make sure you're familiar with the concepts. Thumbs up when you good. So let me take good notes for Alex. He's gonna watch the video, but okay. This is not something I need to do. Okay, so this is just an indication again to show you that like atomic images of what's happening when the correct orientation is occurring. So if I want to form dinitrogen tetroxide, I need to collide in a way where the nitrogen molecules are interacting, because that's where the new bond is going to be forming. So that's why this is the correct orientation, not the nitrogen attacking with the on the oxygen side. So that's exactly what I mean by orientation. It's not like, hey, it's just oriented in space. It's like where the bond, where the atoms are in location to each other. Because if you want to form something with the bond in the middle there, they need to be colliding. Does that make sense? Thank you. Perfect. Totally, the front stuff's kind of easy. This is kind of the new stuff. Okay, so this, did I write on your notes? If you turn to the second page in the packet, the 3A maybe. Not quite. Not quite. Not yet. Okay, but this is something a couple of us refer to in our charades. So rates of reactions in chemistry, we're really dealing with like how fast a reaction is happening, and how do we know? We measure concentration of products or concentration of reactants. Either one will allow us to figure out how fast the reaction is occurring, because we can always make a relative rate of the relationship between them, because we know the balance chemical equation. So I can easily say reactant 1 disappears twice as fast as product 1 forms. So then what would be the coefficient in front of that reactant? A 2, and the coefficient in front of that product would be a 1. So it's all related back to the BCE that we have probably already written for this particular reaction. So we can look at the speed at which the reactants are consumed or used, or the speed at which the products are formed. Which of these rates would be a positive rate? Reactants or products? Products, right. Products would be formed, so that would be a positive concentration change over change in time. That's change in concentration. Bracket, you guys remember bracket means concentration? Okay. Change in concentration over change in time. Whereas the reactants which are being consumed would be a negative change in concentration over a change in time. And that's going to be something we refer to again in a couple minutes. So we're going to really talk about relative rates of comparison, or relative rates of reaction today. Rate laws are something you saw in your reading, and I want you to see it just so you are aware that there are these things called rate laws. And they're written, we're going to talk about them more in depth on Monday, but they're written like this. Rate is equal to K, which is a lowercase k, and it's a constant that's used to determine, that helps you determine the rate of the reaction, and it's different for every reaction, so it's just a value that we can actually calculate, and then times the concentration of a reactant to some power. So this is written very, very specifically. These have more verbiage in it in your explanations. So why in the heck would we care about rates of reactions? Good question. Yes. Right. So you want to know how long it'll take? That's kind of our immediate need. But what about in the real world? Remember your real life and redox extra credit you did? Remember that? Okay, you'll do something similar for kinetics. Yeah.
Like seeing how fast something can decay or like
Yeah.
react with oxygen every time.
Yeah, so like we probably care if we're putting something out in the elements into the world, we care how long it's going to last. Like specifically a structure like a bridge, if we know it's going to react with oxygen and air to form rust, we want to know how fast it's going to form so we can start planning like when we should start repairing the bridge and stuff like that. Fortunately, rust forms extremely slow, but other things that combust, they occur very fast. It's really hard to measure things that occur very slow and occur very fast. We like that stuff in the middle that we can actually sit and watch in time. So that's in chemistry, in AP Chem, we'll be working with things that are going to be manageable in the time that we're here. You guys read, how long does it take, or would we ever see carbon decay to diamond? No, not in our lifetime. It takes way too long. Hold on. I'm glad that you said decay, because we're going to start to relate how does this relate to half-life, to like radioactive half-life in nuclear chemistry, because that's all it is. It's the rate of reaction. The rate of decay is the rate of reaction, and so we actually have a term for it. It's called half-life, to determine how much or how long it takes for half of it to decay. Okay, this is on your sheet. Yes, tell me this is this is on the second page through the booklet I gave you. Yes, okay. And these are all the things that we basically talked about through the video, but there's a couple things that I want to refer to from thermochem first. So we're talking about rates of reactions. In kinetics, are we talking about if the reaction is going to happen? No, we are not talking about the favorability of the reaction. In kinetics, we're saying how fast does it occur because we know it's occurring. We can't really talk about how fast something occurs that's not favorable enough to occur. So these are two separate ideas, but we always will eventually have a way to bring them together. So the first kind of the thought that is it going to actually occur is we refer to the nature of the reactants, and this is on your reading a little bit too. But if the bonds are able to be broken in such a way, then we assume that the reaction is going to occur, so we're assuming that it's thermodynamically favorable. Delta G would be what?
Negative.
Right. So we're going to learn how to relate delta G to K, to other Ks. There's like 2 different Ks in chemistry. We talked about surface area. That's why in the Penny Lab from Honors Chem, zinc that is a dust, high surface area is very flammable. You can rub it on a paper towel and it will catch on fire. But like zinc metal, a strip of metal, you're not going to catch it on fire. It's a huge piece of metal. It doesn't have enough surface area for the oxygen to react with it. We already talked about most of these, but concentration and actually I'll go with concentration first. It's all about the collisions. So the more particles you have, the more likely they're going to be colliding. The more likely they're colliding, the more likely it's going to be reacting. So you always want to be able to explain how the reaction relates to collisions or the frequency of collisions. Temperature has a 2-part to it. Whenever you increase the temperature, you're increasing their speed or their average kinetic energy, and that does 2 things. That increases their number of collisions, so the frequency, and the force. And that's why temperature is so different, because we have to know that there's 2 things that it increases so that we understand how to explain it, because this is one that 2 years ago was one of the lowest scoring questions on the AP exam because people didn't say both. Okay? So star that one or something. And then the general rule of thumb is that if you increase the temperature by 10 degrees, it should double the reaction rate. And that's degrees Celsius. Okay, so just some continued background for now. This is on your paper. So with catalyst, my group did a good job of explaining just the terminology behind it with alternate pathway. But what does that look like? It looks like this. So here is our original reaction pathway. It has a huge activation energy. So we all remember how to label activation energy? Like how many, well, if you know that these are the reactants, the energy it takes to get from reactants to the transition state here, the activated complex, that is the activation energy. So you should know that this huge amount here is activation energy. Do you remember that? Some of us know, draw your graph if you don't know that. So if a catalyst is present, it's altering the pathway because it's allowing for this reaction to occur through a different mechanism and allows it to kind of take on a lower energy activation energy state, but it still ends at the same spot. So a catalyst does not change the reactants to the products, it just changes how it gets there. So it's kind of like the state function thing again. We care about where it begins and where it ends. We don't care a lot about the middle at first, but in the next couple of days, we're really going to talk a lot about what happens in the middle, and that's called a mechanism. So this top part is the original activation energy. The one where it ends here is the activation energy. I'm just going to call it EA prime, and that's with a catalyst involved. So if I have something that occurs from reactants to products, who's to say that it can't be a reversible reaction? So what do I mean by that?
It can go backwards.
It can go backwards. It can take the products and go back to reactants. We will deal with a lot of reversible reactions in the next couple weeks. So products can always go back to reactants. Well, is that reaction also catalyzed, yes or no? Let's take a guess. It is. It is. So if the reaction can go forward through an alternate pathway, it can also go backwards in an alternate pathway, and it's using that same activation energy. It's just a lot easier to go from products up here, because look at that difference. It's a small amount of activation energy needed, so it's probably more likely to go backwards than it is likely to go forwards, just because of the ease of trying to meet activation energy. So this one has a much shorter activation energy than this one did. So we just have to know that they both directions are catalyzed. Okay. We kind of already talked about that. All right. So this is called what? This graph. Do you remember what it's called? From gases? Maxwell-Boltzmann curve. Good. Okay. And for us, that relates to activation energy, meaning how does temperature play a role in allowing for a reaction to occur? Whenever you have molecules that are really fast, so it's the red graph here, they're going to have higher energy, and if they have higher energy, then they are going to meet activation energy more often than the cold molecules that have a lower number of molecules at that specific temperature or at that specific energy needed. So the shaded part here in red represents the area under the curve. That's the calculus thing, right? Pre-calc? You with me? Area under a curve? Okay, so anyway, the area under this curve represents more molecules with appropriate energy to meet activation energy. The cold one has very few molecules at the energy needed to meet activation energy. So that's the difference in how that graph can be used from the gases to kinetics. Okay, I just need a little feedback from you guys. Some of this is review, so I'm going through this. Same graph. Okay. I'm gonna stop this one for a second because this is a well, I'll tell you up front. Basically, reactions don't have a set number of steps they take to react. A lot of times we just write the reactants that we're starting with, and then the final products. But there's a lot of stuff that can happen in between. You can form like 3 or 4 intermediates that would react to form finally our product. So this one is a 2-step reaction. The first reaction goes from reactants, yields a transition state, and you go to this intermediate. And then the second reaction goes from intermediate, goes through this transition state to form the final products. So 2 humps represents 2 steps to the mechanism. And you can imagine there could be like 4 humps to represent the mechanism of the reaction. So we're going to see these more later, but in reference to this question, which step has the higher activation energy? Raise a hand. First or second? First. So you're basically looking at where the reactants start, so the energy that's required to get up to the peak, and this is where the reactants start to the energy it takes to get to the peak. So this is more difficult, right? So the catalyst would most likely you target a catalyst that catalyzing that reaction, so that you would have a lower activation energy, but you'd still end up this intermediate, and then you go through the second reaction. So you can specify, like there's tons of catalysts out there, you can specify the reaction they would catalyze. Okay, this is a quiz question based off what we've already done so far. Read it and tell me what you think. What you got, Lewis? Yes. D. So basically, fine powder has a higher surface area, decreasing temperatures, anti-reaction, decreasing concentration, and decreasing the volume of the solution, meaning you just have less of that solution. It's not decreasing the size of the container, because pushing them together is better than decreasing the amount of a substance. So yes, D would definitely be your answer. Cool. So this is a multiple choice question from 2 years ago AP exam. Nice, right? You can get that one. Totally. You could have got that before you walked in here. Okay, this is going to become the end of me right now, okay? So I've got a couple things to talk about rates, and then we're going to do an activity called All Screwed Up. Because by the end of this, we're going to be all screwed up with kinetics. Okay, so this right here, you might want to write down more of this than you have been writing anything else. This is the relative part. A lot of you guys are listeners. I'm a writer. I have to I write ferociously when I take notes. It's like there's pen is burning on the paper. So do whatever you gotta do for yourself, but write down what you need to here. And you'll see this term called molecularity. So basically, relative rates refers to the relative number of reactants and products that are formed based off the stoichiometric relationships or the mole ratios. I'm going to tell you for about 10 more minutes and then I'll stop, and if I need to finish, I'll finish. So according to this BCE, A plus 2B yields 3C. The rate of disappearance of A in comparison to everything else is, I'm actually going to compare directly to C, is that C appears 3 times, so appears means making product, appears 3 times the rate that A disappears. So it's just according to the ratio in which they exist. Relative rates are pretty easy, but we're going to write them in a different way in just a minute. And you saw this already on your packet. So tell me the disappearance of B in relation to C. Go for it, anybody.
1.5.
So just put it in a phrase like this.
C appears 1.5 times the rate that B disappears.
Okay, so C appears at a rate of 3/2, because it's 3 to 2, which is 1.5, times the rate that B disappears. So I'm going to say C increases 3.5 times, because it's 3 to 2, that B disappears or decreases. Tell me about C in relation, no, we can do this later. So we just know that C is appearing, so it's a positive rate. So you can relate them in a phrase, not only mathematically. Can I go past this? Okay. So this is how we tend to write rate, and I briefly showed you that already, but I want you to see the negative sign here. So this one is in relation to a reactant, and most of the time we are concerned with reactants because they're the things that are controlling the rate. So we generally always talk about reactants. So when you're measuring the rates, you're generally going to be initially measuring the concentration of that reaction to see how it slowly progresses over time. And you'll notice that it is concentration per time, so molarity per second, but molarity is moles per liter, so be familiar with both of these expressions, moles per liter seconds. So let's say we start off with two reactants. We have one molar of each of them. So 1 molar solution of each of them. As they react, what's going to happen to the concentration of the reactants? They're going to go down. Why? Right, they are reacting, they're being consumed to form products. So if we have 1 molar of each of those solutions, they're going to react pretty fast at first because there's a lot of stuff in the solution. But you just told me they get consumed and they form products, right? So what's going to happen to the rate of the reaction as time progresses?
And slow down.
Why?
Because there's going to be less of the reactants and they're going to collide with each other.
Right, so less reactants, meaning lower concentrations. Lower concentrations yields less collisions. Lesser collisions yields a slower reaction. Okay, you got to be able to relate all of those terms to each other. So what should the graph look like if I was graphing concentration versus time? Originally, let's say it starts really fast, it's got a really steep slope. So it's going to be like what kind of graph is that? Okay, or exponential decay, right? Like this. So basically, over time, if you decrease the concentration, it's going to decrease the collisions, and decreasing the collisions decreases the rate of reaction, and the rate of reaction is just the slope of the graph, or the line, or the tangent at that time. So you kind of already understand what's happening behind the scenes, but we're going to kind of put them into more pictures and understand a bit more about why this is occurring. So as time progresses, the rate's going to decrease, like you said, because the reactant concentration decreases over time, so we have a lower rate of reaction. Conventionally, we do like to represent rate as a positive number, because it just, a lot of times when you throw negatives in there, you're like, what does this negative mean? So we generally put a negative in front. You see that negative up there? I didn't really highlight it earlier. There's a negative in front of that rate to cancel out the negative or the decline of the reactant concentration. So we'll add a negative in the front to make it a positive rate overall, because we like to talk about things in positive numbers. So from here, this is on your sheet, this graph. If I'm nice, I think I put it there. It's on the first little quadrant of notes I gave you. So whenever you have a concentration versus time graph, that is the only time when you can look at the tangent at the graph and figure out the slope to get the rate of reaction. It has to be concentration versus time, because that's what rate is. Change in concentration over change in time. So at this particular point, I've selected, let's say, like 7.5 seconds. So at that time of 7.5 seconds, what is the rate of reaction? So you put a dot there. That's the instantaneous rate, by the way. And then you draw your little tangent line. And then you would say, okay, well, from here, I usually try to line it up. So at like 5 seconds, the rate is, or the concentration is about 0.125 molar, right? And at, that's a little far, but right there, at 10 seconds, it's about 0.07. So then you would look at the difference. So 0.07, so this is a negative rate, so it'd be 0.07 minus 1, or 0.125. So I should have switched those, but I'm just going to do the absolute value of the difference there. Divided by the change in time. What was my change in time? From where I looked. So 5 to 10 seconds, so there's a 5-second difference, so 10 minus 5 is 5 seconds. So I could figure out the rate of change based off the rise over run, or y2 minus y1 over x2 minus x1. Familiar with the slope? You can get slope. Okay, so it has to be concentration versus time to do that. But a lot of times in our reactions, I can't say, okay, let me wait 5 minutes and figure out, or 5 seconds and figure out the concentration. Most of the time, that's somewhat unpredictable because it depends on what time you're checking. It's going to vary every single time. So a lot of times we do not calculate instantaneous rate in the lab setting. We will always calculate initial rate, which is at the very beginning of the reaction, what's happening in the first couple seconds, because that slope changes somewhat slower than this over here. So we try to get the initial rate of reaction, and that's what we go with for our rate of the reaction. Okay, so pretty sure I just told you all that. I want to explain a little bit more about what happens to the slope as it goes towards the end of the reaction. But in this particular graph, start here. This green line represents the reactants versus time. What would the graph look like if I were measuring products over time?
It would be exponential.
So would it be like this?
Oh no, it would
Be like this. So it would have a little initial curvature up and then flatten out. So this one I'll keep in green. It's going to kind of keep extending out. It's going to get slower and slower and slower and slower. When I say slower, what's happening to the slope? It's going towards, it's approaching zero. It's approaching zero. So slower means the slope approaches zero. When the slope is zero, there is no change over time. So the rate of reaction is supposedly zero. It's usually not zero. It's usually going to be altering back and forth. But the reactant, that's what the reactants look like. The products are going to increase slowly, and then they'll level out as well. But they're going to start to level out at exactly the same time that the reactants level out, because the reactants make products. You can't make products out of nowhere. So in these two situations, at this point, about here, is when I started to level out. At that time, this is called equilibrium. Okay, the reactants and products are back and forth, back and forth, back and forth, back and forth. But in the end, if I give you $1, you give me $1 back, nothing happened. But did something happen? Something happened, but overall, nothing happened. Right? So there's no net change. So equilibrium is when there's no net change in the concentration. But kinetics is really concerned about this part of the graph. Our next unit is concerned about that part of the graph, but we're going to see how they are related. So the slope of the positive line, or the product line, is going to be a positive slope. So I think I explained all this. Do I need to explain anything more here after you read? No. Instantaneous rates at a point, at the tangent at that point, and then eventually equilibrium will occur if the slopes stop changing. Okay, trying not to bore you to tears, but the first part of this is a little bit, we got some stuff going on. Okay, so according to this reaction here, tell me or explain why these graphs do not have the same slope. These two graphs. Lewis. So they're forming twice as fast as reactants are being consumed. So you'll see the reactants have this kind of more gentle slope, and then the products have a pretty extreme height change and slope change. So it's more steep, that's what I'm looking for. So it's steeper because you're forming twice as many products as reactants you're consuming. So this refers to both hydrogen gas and separately iodine gas, and this is formation of hydrogen iodide. So we're going to learn how to compare them graphically and mathematically. Okay, how much more do I do right here? I have like 2 more things. Okay, I'm going to stop for a minute after this, and then we're going to do our lab. So this is the reaction that this is our generic reaction. Whenever you're looking to express rates in a relative form, relative means in comparison to the other reactants and products and according to their BC, their coefficients. So generally, we would write it in accordance to their personal coefficient by putting the rate is equal to the negative 1 over its coefficient times the stuff that we already talked about, the change in concentration over the change in time. So this coefficient is going to be whatever the this A is going to be whatever the coefficient is for that particular reactant or that particular product. And so this is kind of still relating them to one another, but we sometimes call this relative rates, we sometimes call this absolute rates, because the absolute part of it comes into the fact that we actually have a number for this. We can have a number for that, like, 2 molar per second. It's going to be changing by 2 molarity per second. So I'm going to come back to this after you write down that, and I'll finish that at the end of class. Okay, whenever you're done writing that down, I am going to finish that. Go to your packet, first page. Okay, so this is an introduction to how does the concentration of different reactants relate to the rate of reaction. But sometimes one reactant is very, very important in controlling the rate of reaction, where another reactant is lesser important to the rate of the reaction, just because the type of reaction it is. So it's called All Screwed Up, and you guys have these little baggies. But for part one, you're basically measuring the rate of the reaction where you can take the nut and you can screw it on the screw and how fast you can do it. And then you're going to be graphing this in accordance to whatever the paper says. You guys have it in front of you? Yes? Okay. Graph on that paper. If you can fit it on there, you'll be able to answer most of these in class. So we have I'm going to give you guys about 30 minutes to get part one and part two done. I'm not going to give you a whole lot because it's kind of inquiry to make sure that you can understand conceptually what's happening. Same groups that you did earlier, because I have 5 bags. I didn't have enough screws for some reason to do 6 screws. Okay? So get your groups, come see me. I want you to follow these to the T. Okay?
Our wolves.
Follow these trees to T. And if you're looking at the Okay, so if you need a container to pop the combination in afterwards, you'll hold them. I didn't need the leaders on. So follow the directions to a T. Times you're going to need a phone or something at the time. You have time in between. Okay. So you guys are creating the rotation process. So they all have to be the same. So the goal is to get all the screws or nuts on the screws as fast as possible, but you're rotating so you have different people doing it, not at the same time. So like you do one and then I do one. Yeah. But it only has to go halfway. So is it just the time? Is it all the total time for us to finish all of those? Or is it time that we can? So every time I say one, like it's done. Wait, I just want to try one yours. You can map the time and you can get the value, the time it takes
minutes for each one to be out of this. Let's go.
Yeah, we were.
Okay, good. When you say done,
Should I leave it like this? Go, China, go. Go, China, go. Come on.
See, Kevin? See, it doesn't sound.
Hold on, stop it.
This is my phone time, ready? It's on.
Wow, minute 32.
What happened to me?
We unscrew them again?
So, for the first screw,
We're going to be adding We could just like I thought you said, alright, time. You should. That's just it.
So who was the right determined step?
When you start with 10 and 0, but then
Just grab it on your paper.
I took a screenshot.
We know how to do it, so we have No. Wait, are we supposed to be adding simple units? It doesn't fit.
Oh, you know, some of them what are we gonna write?
So if it doesn't work, we drop it.
There's no way to tell.
Okay, guys, I want to see this round 2 and then in the next 5 minutes.
Maybe it's in the middle, so we don't have to keep it there. Wait, take the ones that you can start on, yeah, when you got one of
Leave them on the leave them on the next one.
No, you're doing it.
Just like 30 minutes to make these guys, okay? And I'm not going to do that.
Five minutes.
Come on, China. It's really
We're losing a
At the end, I think it's going to take forever. As we get further, it's going to be a lot more. There's only going to be one
It's gonna be impossible getting the left one. It's gonna be tough to don't fit.
Here we go! Done. A minute and 20 seconds.
There's tape on my forehead and it feels weird.
Stop, no, you just made it worse.
You want to feel something.
It's the last one. If it
Alright guys, make sure everybody gets data, everybody's graphing. I'm gonna give you guys 9 more minutes in the lab. 9 more minutes so you can get your data. Yeah, you can do that. I can do that. I just want to give you Some of these things are group efforts, so I would let somebody go ahead and start listing the steps of the reaction, which steps you think took the group the longest, represents the slowest steps, stuff like that, because they're going to be kind of a conversation. Those are the ones you need to answer as your group. The graph really can wait. You have to find the R-squared value, but you can start with the other value.
Alright, well, we need to find out. Yeah, how do you do those words? Something else that they, it's not working on its own. You gotta turn your light on. No, I don't know. I don't. There it is. Alright, you ready? No. 9, 4.
Alright guys, I want you to get that whatever question you're on done. I want you back up here in a minute. 1 minuto.
The number 2.
Is that like the whole
Alright, come back to people. Now.
Sorry, I said
Should I put these back in the bag? Is that not good? Did I put this in the table?
No, it's fine, I'll grab it. Okie dokie. So, what you should have seen were some similarities between reaction rates, collision theory, and stuff like that in your reaction that you just did. You will finish those questions for me, and I will give you some time at the end of class, but I want to finish this up first. It'll take me about 5 to 8 minutes, okay? So, stop talking to your group members for a second. You guys can talk in a second. This is finishing up absolute rates, relative rates, and how to actually put numbers in and calculate. We'll do rate laws next week. But I saw some people's outlines. I didn't see everybody, so turn in late for a 90. But I'm expecting that you have some general knowledge because I'm speaking a foreign language right now. It's not. Okay? So, when you're talking about the absolute rate in comparison to the reactant, you are comparing it to its ratio because that's how you determine how fast it reacts. Because if something reacts twice as fast as something else, it's because it has usually a 2 coefficient and so forth. So then how would you write it for D? How would you write the same rate for D, for product D?
It's little a, little d. Big
So
O.
what sign goes in the front though?
Oh,
A positive sign, so it's product, so it's making product. So 1 over
Little d,
lowercase d times,
delta
so
D,
change in
delta time.
concentration of D over change in time. Okay, so whenever I do this though, I'm going to get a different relative rate between A and D because these coefficients are not necessarily the same. So it looks like the rate is different for the reaction, but it's not. The rate of the reaction is one standard rate. It's going to be whatever the rate of the reaction is. But in comparison to a specific reactant product, when you talk about it in that perspective, the rates for every single reactant product will be different. The rate of consumption will be different than the rate of production. So those are going to look different, but no matter which in the end we're looking for, the rate overall for the reaction is based off whatever the data says in the lab experience. So
we're going to be looking at that. We're also going to be looking at comparative rates, which is what we did earlier with like this reacts twice as fast as this, so it's a relative rate as well. So this is just something to be familiar with when you're writing them out. So this is what that information I want you to use to write the information about nitrogen or dinitrogen tetroxide yielding to nitrogen dioxide. So how does the rate of formation of NO2 compare to the rate of disappearance of N2O4? You can just tell me relative first. So the rate of formation, go for it, hon.
The rate of formation of NO2 is twice as fast as the rate of disappearance of N2O4.
Okay, so then how would you write? Well, this one I'm good with the relative because it's actually it doesn't say express it as a specific way. So if it's a relative rate, you can explain it. It's twice as fast formation than the rate of consumption of that. That's fine. It's just because the ratio is a 2-to-1 ratio. Everybody got the relative part of that. You can explain verbally how that relates to each other in terms of production and consumption. Okay, tell me how we would write the expression for these two. Okay, so, oh, what? 855.
Maybe
Maybe
they
skip it now.
changed the value.
Yeah, we have 10
Maybe they
minutes.
changed them now.
Yeah. Okay, I was like, no. All right, so write the rate of expression, or the rate expression in terms of the disappearance of the reactants and the appearance of the product. So tell me what I would say rate equals to in terms of this reactant. The expression that I just showed you how to write. Ready when you are. Negative sign. 1 over 2.
It's a concentration of
NO2 over delta T. Okay, so do that in terms of oxygen. 1 over 1, because the coefficient is 1, times delta oxygen over time. Okay, just making sure you understand when I ask for expression, that's what I'm asking for. And I'm not saying rate law, I'm saying rate expression. So that's going to be different than a rate law we write next week. So this one, you guys could say a negative 1 over 3 and a positive 1 over 2. Okay, so that's how we write the expression. How would you relate that to an actual rate that's given to you? So this is the rate given to us. That at given temperature, the rate of appearance of ammonia is that molar per second. Do not say meters per second. I know it's an M, but it's molar per second. What is the rate of consumption of nitrogen in this case? So first we need to write out the BC. So if we're forming ammonia, what's BC? Okay.
3 on the H2 and 2 on H3.
3 here.
2.
No, that's good.
That's right. Okay. Okay, hold on. I'm assuming some of you guys are different. Okay, so if the rate of appearance, you'll notice this information is in reference to the perspective of ammonia, then how would the other ones be written? Or how would you adjust the rate? Tell me verbally first. Compare nitrogen to a formation of ammonia. So nitrogen or ammonia forms twice as fast as nitrogen. So if ammonia is forming at the rate of 2.0 times 10 to the negative 3, what would a nitrogen's disappearance be? 1.0, right? So you mentally just like, oh, it's half the rate, right? Well, there's a way to do it. It's 2.0 times 10 to the negative 3 molar per second is the rate of appearance of ammonia. But in comparison, you react 1, and I'm going to kind of write it like a mole ratio, 1 nitrogen per 2 ammonias. So that's why you half it. Because the rate should stay the same. It's the same units. It's molar per second, but it's 1.0 times 10 to the negative 3 molar per second. And it's the rate of consumption. So we write it as this because we don't need to indicate the negative sign because we're saying the word consumption. It represents the decreasing of the matter. So then what would hydrogen be?
3.0.
So what's the ratio?
3
3 over 2. So 3 over 2 would create a 3.0 instead of a 1.0 times 10 to the negative 3. So it'd be this still times 3 hydrogens over 2 ammonias and give us 3.0 times 10 to the negative 3 molar per second. Okay, that's it. So that's relative rates, kind of absolute rates, some stuff with graphing. We will use graphs a lot. So please make sure you're paying attention to the units and the axes on these graphs, okay? So you just have a little less than 10 minutes, work on the all screwed up, and then
Under, last night I had to go through a lot, okay? I want you to answer some questions on that. On your active reading guide, not the reading guide from last night. That was like the NSMI, just basic reading, background information. Under active reading guide, chapter 13, which is Kinetics, is number 13 through 21. Okay? So finish your activity and then do that for me. And I'll name the questions that you want to do. I haven't seen everybody's yet, so keep your outline. I did see yours actually. I just have to mark it down. Give me a second. 13 through 21. Please use your time wisely. If I'm giving you time, muchas gracias. Um, 13. You can do it, little guy. It's not gonna be great.
When it says 10 screws left, does that mean we take the time before we screwed on the screw, which would be 0, or after?
0.
Okay.
Oh, let me stop video.